Peter Corke's presentation on robotics began by reminding us that robotic technology is almost 60 years old, but the best is yet to come. Robotics has revolutionised the manufacturing industry, but its uptake in many other industries has been limited until now. Robotics are now a commodity technology and have driven productivity and quality growth in manufacturing and logistics. Artificial intelligence, and in particular computer vision, has dramatically increased the field in which robotics can be now deployed. His talk covers robotics, artificial intelligence, computer-aided vision technologies, with particular emphasis on what it means for the food production industry. So please enjoy Peter Corke's presentation.
Live in Brisbane, but I was born in Melbourne. I grew up on a small farm in central Victoria near Castlemaine. Been doing robots for a very long time. I was taken by some pictures in Andrea's presentation earlier about how countries rise to natural challenges. And there's some pictures I took of a tomato greenhouse in Iceland. So geothermal energy in and tomatoes out. A quite extraordinary thing to see. I'm going to talk about artificial intelligence and a particular subset of artificial intelligence, robotics, and how it relates to food production. So I'm going to go very quickly through what artificial intelligence and robotics is, perhaps disabuse you of a few notions you might have about robots. They're not as good as you might think they are, and it's kind of sad, but it keeps researchers like me in business. And then talk about some specific things that we've done applying robotics and AI technology to food production in a number of different sectors. So, start off about artificial intelligence. It's much older than you think, right? It's way before Google. So it actually is probably a technology is about 60 years old, actually. But for the longest time, it was limited by the power of computers that were available to them. So it's only in recent times that it's really got into its stride. But we've made stunning progress in those 60 years. So we beat human grandmasters in chess, well over 20 years ago, and just a couple of years ago we beat human grandmaster in the Asian game of Go, which is much, much harder than chess, right? So in terms of things, if you measure them in there purely in terms of intellectual complexity as human beings perceive them, AI is much, much better than humans in that. AI is now really good at understanding spoken language, right? So anyone here got an Alexa device or a Google device or an Apple device at home? Yeah, not great, but they're getting better. AI writes a lot of articles now, so a lot of short articles about financial information or sports information. So you get a data feed comes in and articles go out, and they go out onto the wire services and get published for humans to read. There's no journalist involved here. It's outsourced to an AI. AI is pretty good now at understanding what's in an image. So I can go to Google Photos and put in the word ships. I like ships, and out will come all the pictures I've taken of ships. That's pretty good. I don't have to file them away right into all these different folders, a ship folder and a submarine folder and an Iceland folder, right? It does it for me. AI is starting now to be able to understand the activity in an image. And this is still in its infancy, but it's pretty impressive. You give it a picture, and it says it's a man in a blue wetsuit surfing on a wave. It's probably what a human would say if asked to describe that picture. So AI can do this now as well. So we're starting to be able to interpret what's going on in ways that are meaningful to humans. We've only been able to do this perhaps for the last 5 years. And what's pushed this? Absolutely, computers are getting better and better. There's a thing called Moore's Law, which is plateauing off, but we've got other ways of doing computation in parallel that's helping us here. Much better algorithms. So the computer codes that we use to process the data, we've made huge strides and insights into the way they should be designed. And then there's just a ton of data that humans create, come from our cell phone cameras, from Facebook, from all sorts of photo sharing websites, from IoT devices that these AI systems can learn from and then make inferences and predictions. So that's what's driving this revolution. And it absolutely is a revolution. Now, when AI was first conceived in 1956, robots weren't on the picture. they hadn't been invented yet. It was a term from fiction, but robots as machines that do useful work did not exist. First robot company only came into existence in the late 50s. They shipped their first product in the early 60s. So again, that's a technology that's nearly 60 years old. Robots today are almost commodities. So on the left-hand side, you see robots at work building Tesla motor cars at a plant in California, in Fremont. And robots are fantastic, they're reliable, they can lift heavy things, they don't get tired, they don't do their backs. So there are a lot of advantages for people in the manufacturing industry. And robots have thrived in the manufacturing sector because they can work really well with objects that are regular and organized. They don't do so well in the world we inhabit. That's the current research frontier. What you see on the right-hand side is an Amazon fulfillment center, and there are shelves of Amazon product being toted around by robots. And the shelves are brought to human beings who reach into the shelf unit and pick out the object the person ordered and put it into the cardboard box, which gets shipped to you. So the robots are really good at picking up the shelves and moving them around the warehouse. Much faster and more efficient than human beings walking around the warehouse doing that, or on electric scooters or whatever, right? But robots are no good at trying to understand, say, the task is to take the toothbrush out of that shelf, to recognize what's a toothbrush, to reach in, pick it up, knock other things out of the shelf and put it in the box. Wickedly hard problem. And Amazon employ humans to do that because robots can't do that. If robots could, Amazon would be using robots. Amazon have got probably hundreds of thousands of robots in their fulfillment center. Amazon is an amazing company. It's an IT company, employs a lot of robot technology, and a side effect of that is that they ship stuff to us at a very low cost. So robots, as I said before, are huge penetration into the manufacturing sector and now into logistics, shipping, the Amazon example. We don't see them. They're missing in action in a lot of other sectors, in healthcare, in agriculture, in construction. And you say, well, what's common about all of these applications where robots are not? And it is that they are somewhat chaotic, disorganized compared to a well-organized factory environment. And I'd also say that almost all of them can be done quite adequately by human beings, can be done brilliantly by human beings, and the human beings are using their eyes, right? They're looking at the world, they understand it, they've got experience, they can reason about it, and then they do things with their hands or their feet, right? If you're driving a car, you're looking with your eyes and you're doing stuff with your feet and your hands, right? That's what you do if you're a driver. Robots are not very good at understanding the world as it's perceived, not yet. And so this is I think the surprising truth to a lot of people. The robots today are actually not very good at understanding what they see. They're not very good at picking things up and manipulating them. They don't have hand-eye skills that are anything like ours. So although a computer has been able to beat a human grandmaster at the game of chess for more than 20 years, we don't have a robot that could do what that kid's doing, which is to pick up a chess piece in a graceful and smooth and successful manner. That's cutting-edge robotics research. Surprising, but it's true. And vision is this really powerful sensor we use every day for all sorts of things. We use it for driving. We can do really fine, dexterous stuff with our sense of vision, right? Robots don't have our visual intelligence, and that's what's holding them back. So I lead an ARC-funded Centre of Excellence called the Centre for Robotic Vision. Our mantra is to create robots that see, and I'll give you some examples as we go about the sorts of things that we're doing. So we've been in business since 2014, big investment in dollars. We've got a lot of very smart people, and we're trying to create instances of robots that use a sense of vision to do a useful thing. That's what we're about. So this is one example, and it may look a little clunky to you. We won a competition last year sponsored by Amazon, which was to solve this last problem that they have of how do you reach into a box and pick up a particular object. It was an international competition, and our team came first. So we beat a lot of very famous international universities like MIT and so on, which is very pleasing. So this robot is able, you can ask it to pick up the teddy bear. It will find the teddy bear. It will choose the right tool, either a pair of fingers or a suction gripper, to pick that object up and put it into the appropriate output box. It's slow, it's not graceful. Humans could probably be perhaps a factor of 10 times faster, but starting to show what it is possible to do by combining a sense of vision with artificial intelligence with robotic manipulation of its world. So I'm going to talk now a little bit about food production, and Garshan's given me a very nice introduction, so I won't belabor this. We have issues with global population growth, which is shown on the right-hand side there, a number of different future scenarios, and the consequences of global warming, which is in terms of sea level rise, which is going to remove land from agricultural production, and the rise in temperature is going to affect the way crops grow. And the carbon dioxide concentration will also do that. We've also got this issue of the aging population. So this bar graph shows what's called the dependency ratio. It's the number of people who are not working, so kids and old people, divided by the working age population. And you can see at the moment, we're in a sweet spot. That's as good as it's ever going to get. And from here on out, the population is going to be increasingly old. More young people and old people have to be looked after by a smaller number of working age people. So we're going to have a productivity problem into the future, and that's a gap that robotics can step into. So I'm going to talk a little bit about some work we've done in broadacre production, and then some work we've done in horticulture, and a bit about animal production. So food production has been driven by a number of revolutions. Genetics, there's been a lot of advancement there, mechanization over the years, and herbicides and pesticides, right? This is what's allowed us to feed the planet despite the growing population. We can feed the planet, or big wealthy countries like the US can feed themselves with a very small fraction of their population now. And this is what's driving the trend towards urbanization. We don't need people on the land anymore to produce the food that we need. That's a massive, massive achievement. And over time, our agricultural equipment has become bigger and stronger as we've changed the motive power source that we use. But there's been side effects of this, adverse side effects. So one of them is that as machines get bigger, the ground pressure increases, and that's going to damage the crops that the machines are rolling over. Now we can solve that problem by using controlled traffic farming, GPS, navigation. The farm gets turned into this very techie environment, and the machines roll up and down roadways through the field. So we have a solution to that. Another problem of having poured herbicides on weeds for 50 years or more is that they've developed genetic resistance, and this is a thing that worries broadacre production people a lot. What do you do about weeds that you can no longer poison? And so I got asked the question, why is it the machines have got bigger over time? And it's because of the driver, right? If you've got a driver and the driver costs you money, you want to make that driver as effective as possible. You put him in a machine, him or her, in a machine that's as wide as possible and as fast as possible, right? And is big and carries a lot of stuff. So it's because we have the human in the cab that we've been driving machines to be bigger and bigger, and there are adverse consequences of that, and we've hit a limit. It's hard to make the machines too much bigger. You run into mechanical issues. So we asked the question, could you do it by having lots of small machines? And these small machines don't have drivers. The economics doesn't make sense if you've got lots of small machines, each with a driver. The economics is worse, not better. But if they're all autonomous, then you could divide the work up a lot across lots of small machines. They've got lighter ground pressure, perhaps do less damage to the ground. The self-driving technology is around. It's becoming a commodity. I'm sure in 10 years' time we'll see this stuff on the roads, lots of experimental vehicles, self-driving. We know how to do that. And so we figured this problem of driving an agricultural machine is basically one of interpreting visual information and controlling the machine. It's a robotic vision problem. So can we do that? And so we partnered with a Queensland-based company called Swarm Farm and Australian Centre for Field Robotics, and we developed a vision-based navigation system for small agricultural robots. And we used vision and a lot of software to reduce the hardware cost of that particular platform. And that's a sort of aerial overlay of the machine's driving navigation capability. With this machine then, we added downward-looking cameras. So as we're driving over the crop, we can recognize individual plants, detect the plants, and then classify them. And once we can do that, once we know what plant is what, then we can decide what to do with it. Is it a good plant or a bad plant, friend or foe? And if it's a plant that we don't like, then we can do targeted spraying on that particular plant. So we can reduce the amount of herbicide dramatically. But if it's a resistant weed, then this isn't going to do it. So you use a different actuation technology. You hit them, you chip them out of the ground. So you're not doing ploughing. It's close to zero tillage, right? But we can remove weeds that are resistant to herbicides. And there's people doing research in all sorts of ways of destroying weeds. There's flames and microwaves and all sorts of funky things. So there's more than one way to kill a weed, right? The other thing we can do with our robot as it's rolling over the ground and taking pictures is we can actually build those into what's effectively a photo mosaic. So by rolling over the ground, we can build this lovely map. We can get statistics about where the weeds are, perhaps learn something about the ground in which we're growing. And we've done some stats which show that there are big savings in terms of energy and labour and herbicide by going to this multi-robot approach. All right, quickly, horticulture. Another really big sector of agriculture in Australia, and we suffer a lot from labour shortages to get the right people, the right time, the right place. And so this is a robot that we developed called Harvey, and it's targeted at capsicum picking. So that's the robot. Here it is in an indoor greenhouse environment. And this is the robot's eye view of the fruit. So there's a camera on there which is building up a three-dimensional and colour image of the fruit. On the right-hand side, you can see how the robot perceives it. And it's moving around to get different viewpoints and to eliminate effects due to leaves. Comes in, grabs it with a suction gripper, cuts the stalk, the peduncle, and there it is. It's much slower than a human, but it's relentless. It will go night and day. And remove capsicums. So it's something we're pretty proud of. We deliberately chose the capsicum because it's quite a robust fruit. I mean, this approach is not going to work on a tomato. It's not going to work on a strawberry, right? But we grow a lot of capsicums, and they're robust, and this would be very, very suitable to that. This is some work one of my colleagues has been doing with Agriculture Victoria and some others using drones and multispectral imagery to detect phylloxera outbreaks. By flying over with a drone with the right sort of camera, the right sort of AI and image processing, we can localize where this disease is. And it's much more productive than having human experts on the ground doing this kind of survey work. We can do in 16 minutes what takes an expert a day. So huge productivity win there. Animal agriculture is, until it's replaced by lab-grown meat, and there probably will always be a boutique demand for meat from animals. I was involved in some work when I was at CSIRO in the early 2000s on what can we do technologically to eliminate fencing. Fences are a huge cost input in the raising of animals. And so we did some work in the video on the left-hand side shows a couple of things that we did. One's a thing called virtual fencing, and this is a meme that's been around for a long time. We did a lot of quite rigorous experiments looking at virtual fencing. That red line is just something I drew on the slide. There is no actual line there. But the animals are wearing collars that influence their behaviour. There's another one we did where the triangles represent bulls and the circles represent cows. And you put more than one bull in a paddock, instead of looking after the cows, they fight with each other. And so at the top there, we look at their positions over time, figure who's the aggressor, and jolt the one who's charging another bull and influence their behaviour. And this is some other early work we did using drones to push cattle around the landscape. So instead of having heli musterers or people on quad bikes, we can use drones. And the animals are curious for a while, and then eventually they back off. So drones are a commodity tech, very, very low cost. So you could use swarms of drones sufficiently coordinated to move animals around the landscape. So you don't even have to put devices on them. We could do it using drone tech. Lots of other applications in animal raising, preparing, delivering feed, and also monitoring what the animals are doing in a feedlot. Phenomena like shy feeders, animals that are diseased, sitting back. You want to get them out of there quickly before the disease will spread. I want to talk about some work my centre's done on a robotics roadmap. So we've tried to understand what would be the benefit of robotics to Australia as a country. And Andrea talked about agtech, and I think of agtech as a vertical. Robotics is a horizontal, all right? It's a foundational technology that can be used in many sectors. So we have this report. There's like the 400-page version, the 30-page version, and the 4-page version. So I'll leave them here for people who are interested. That's the website. But the findings are that we are very underinvested in robotic technology in this country. We need to improve our productivity if we want to maintain standard of living. Robotics is one way we can do that. Agriculture is one sector that robotics can feed into. There are many other Australian sectors. Do really good things to our economy if we could adopt robotics more. So we've gone around trying to understand what's blocking the uptake of robotics, and we've made some policy prescriptions, if you like, that we hope that a government at either state level or federal level would take some heed of. But issues like investment is one of the things that we believe holds it back. Venture capital, availability, all sorts of the ways the R&D landscape is tilted also affect this. This is my last slide. The take home from this very rushed presentation, the capability of automation for working in the field, not in the factory, in the field, right, is increasing rapidly. So sort of open your minds to what it is that robots could do perhaps in your area of endeavour. There are opportunities all through the food chain, right, from on the farm through to food processing facilities. And I think robots can help enable new modes of food production. So the thing in the picture in the background is an artist's impression. It's not real, but it shows a kind of futuristic city where you've got vegetable pods on the sides of buildings being manipulated by giant robots. So we could imagine new ways of creating food, perhaps closer to where it's being consumed, inside all that unused space on the sides of buildings, tops of buildings, etc. In the future, when we have autonomous cars, all those car parks in the cities, we can turn them over to food production with grow lamps, right, and hydroponics. So all the benefits that factory people have got from robots, quality, productivity, addressing the scarcity of labour, robotics is going to help those problems within agriculture. Stop there. Thank you.